Okay, so I think I will begin. So my plan today is to prove the factorization theorem and then move on to the flat projective connection. Let's see how much I achieve. So the setting is that sigma p is a S-pointed curve, as always. With a node at Q. Of course, Q cannot be one of those P's because P's are supposed to be smooth. So, and it may have other nodes, I don't care. So now we take the sigma twiddle to sigma, and I just normalize the point Q. So I'm going to put Q prime and Q double prime here. So this is normalization at Q. And now there are smooth points here. So I'm going to choose one local parameter at Q prime, I'll just call it Z prime, and another local parameter at Q double prime, I'll just call it Z double prime. So they are local parameters. Okay, so now what we want to, so factorization theorem. So what it states is that if I take V of sigma with respect to P and lambda, so lambda is attached to P. So these are dominant integral weights for the affine case. So this is isomorphic with V of sigma twiddle, and I am going to take P and then I will put Q prime and Q double prime, and then I have lambda, and then I'm going to put mu star and mu, and sum over mu in DC. So just to remind that DC was the set of dominant integral weights for the affine Kac-Moody Lie algebra and central charge C. And I have C fixed once and for all. So that's the factorization theorem. The important consequence of this theorem is that you are calculating some object here on a genus G curve, and here it has become a genus G minus 1 curve. So you are calculating this dimension for genus G curve. This is now genus G minus 1 curve, but you pay some price by adding more points and more weights. But in any case, we will come to that probably next time. That so this whole thing reduces to a genus 0 problem, and further it reduces to genus 0 with 3 points, and the rest it comes from some algebra, which I will explain next time. Now this map is induced by the following map. Right. So this map is so this map, okay, I just have to remind one more thing. So we had this so if I take M a representation of G hat, then I define this Dm, and it is nothing but the restricted dual. So this is the restricted dual. And that is nothing but you take the weighted space edge here, and you just take the direct sum of the duals of the weighted space edge. I mean, as we talked last time, so this edge slightly more categorical explanation or formulation, but the action I'm going to twist it. So now this was, let's say, I'm only dealing with a highest weight representation. So then it's direct sum of weighted spaces, and I just take the dual of that. And so this becomes a lowest weight representation because I'm taking the dual of that. And so we just change the action by taking it x minus, sorry, I denote it usually by x and v. And this is nothing but x tensor Tn, Jn, whatever. I mean, I keep changing my local parameter. So, so this is x minus n acting on v. So this has the effect now that I've changed it back to a highest weight module. So this m check made it lowest weight module, but now I'm changing positive to negative and negative to positive. So this becomes a highest weight module. And if I take d of h lambda, then it's very easy to see that it becomes h of lambda star, where lambda star is the highest weight for v lambda star. Now, v lambda was the highest piece in h lambda. So this is the finite dimensional irreducible module with highest weight lambda, and I'm taking the dual of that. And this also is say by minus of w naught lambda. So w naught being the longest element of the finite while group. Okay, so what is this map? So this map sends h to h tensor. Now I should, yeah, maybe I should write it here. So this h as the highest piece, I have v of mu star here and v of mu here as the highest piece. And I am taking, of course, direct sum. And this map so this map is nothing but h going to h tensor, and I will just write I mu, where now you see v mu star tensor v mu is nothing but end v mu. So v mu star tensor v mu is nothing but end of v mu, and I take the identity of element there, x going to x. So this is the map. Now this map factors through this one, and the reason is that
Sorry,
yes, absolutely.
the identity is in some kind of. So I'm just worried these are big vector spaces, right?
Right. So you see here h is going to h. So this is h is going to h tensor, an element here. But there is a distinguished element here, which is the identity element. I think of this as endomorphism of v mu. And this is the unique gene variant, if you like.
Sorry, I just have a naive question.
Yes.
Does that live in some kind of completion of the tensor product?
No. It's finite dimensional.
Oh, v mu is finite. Sorry.
Yes, v mu is finite dimensional, so no completion.
Okay, you must have said that. I just.
No.
Sorry.
So v mu is, so I have kept this notation. V mu is irreducible module for the finite G.
Yeah. Sorry.
And that's finite dimensional. H mu or H lambda, I have reserved it for representation of the affine algebra.
If a representation of G and its dual, then you view it as a representation of G double bracket T and the center, then you induce the full feedable parenthesis T and give those P's in it.
Yeah, exactly. Yeah, exactly. Right. So right. So I was saying that this map factors through this one, and the region is the following. Let's see. So the factors means, so we have G of sigma minus P acting on H lambda. 2, now you have this H lambda tensor H mu star tensor H mu, and divided by G of sigma minus P union Q prime Q double prime of the same thing. Now let's observe that this, okay, so I should say, so right. So we have a map from sigma minus P to, no, the other way around, this way, sigma twiddle minus P twiddle and Q prime. No, I just want this. Right, we have a map like that. So this gives me a map C sigma twiddle minus P to C sigma minus P. Okay, but then there is a map this way, just the restriction map. Oh, I'm saying it correctly. No, I am definitely not saying things correctly. So this is a map here. So this is a map here, and then now it is correct. Sorry about this. So now it is correct. Okay. So this gives me a map like this. By putting identity on the Lie algebra factor. And now observe that this map H going to H tensor I mu is a map which respects the G of sigma minus P hat action through this one. So this object is acting on this space. This object is acting on this space. And I'm saying that this map, which I gave, respects this action through this thing. And to see this, see, I mu is only happening in the highest weighty space. I mean, in the top piece. And this I mu is solely in the top piece. And I'm taking a function which has no pole at Q prime and Q double prime. So the power series expansion will only involve positive powers of T and maybe the 0 power of T also. But this element is a G invariant. So this will be killed by the G action also. So that means that this map really goes down to this quotient. Is this point clear?
Yes, so you use that the image of this map C to you go to things which has no pole Q prime and Q second and also are equal.
Exactly. That's exactly what it is. So this we get a map like that. And now the theorem is that this is an isomorphism. So this explicit map is an isomorphism. So theorem. And let's call this map something, although yes. So I am going to call this map. Okay. So this map I'm just going to call F hat, and this map I'm going to call F. So F is an isomorphism. Okay, so that's the theorem. So I'm going to prove it in two parts. One part I will give more or less full detail, and for the other part I will say at least what the main idea is. So first of all, we prove that F is surjective. And then one will have to prove that F is injective, but let's first prove the surjective part. So surjective part means what? That if I take an element here in the quotient, then it's really coming from the domain. I mean, okay, I'm just saying the obvious thing. So I'm not making any serious statement here. So, okay, so I'm going to do it in parts. So the basic idea is that, okay, so first let me tell you the basic idea, and then we will go through the details. So the basic idea is I take a vector here, and somehow I want to approximate that vector here and move this to really here to I. So that's the idea. That I'm going to take a vector here and I'm going to move that to a vector here using this thing and this thing. So that's what I'm going to do. Okay, so right. So for any n bigger than 1, let's pick a function gn. So let me write it and then I will explain. Fine. Let me write and then I will explain the notation. Gn at q prime minus z prime to the power minus n is congruent to 0 mod z prime. Okay, so what is the notation here? So we want to pick a function, a global function. Global function means global here. And this notation means that it vanishes at q double prime. So let me write it. Gn at q double prime is q. So we want to construct a function. So I'm fixing n. And now we want to pick a function gn here in this affine coordinate ring. So this is function defined here. So possibly with pole at p and q naught prime, but vanishes at q double prime with this property. So I have a pole of exactly order minus n, a pole of order n, and there is no other negative power. And it's mod z prime. So that's what I want to pick a function like that. And so let's observe that sigma hat minus p is an affine variety. Because after all, this was normalization of sigma minus p. So this is an affine variety. So I remove one more point. It's still an affine variety.
Sorry, I forgot. What is sigma hat?
Sigma, sorry, you are right. So this is normalization at that one point. So now, since it's an affine variety, I can make such a choice. Right? Okay. Now, so what does it have a consequence of? So then, let me write it and then again I will explain. Okay. H is V1 X G and H tensor V1 tensor V2. X minus n 1 Notation. Oh, thank you. Thank you. So what is the notation here? So H, V1 and V2. So H is in H lambda. V1 is in V of mu star. And V2 is in U. And X is arbitrary element of the Lie algebra. So X is in G. So I'm applying this here. So this, of course, I mean, I just have to do component wise. So here I get, so I applied it on the first one, and then I apply on the second one. And keep in mind that G and Q prime has the property that it has only Z prime to the one negative power, and then it's mod Z prime. So rest is divisible by Z prime. And I'm taking a vector in the highest weight piece, So that will be killed. So there is no contribution. So only contribution will come from here. And there will be no contribution coming from here because the function has no pole at Q double prime and it vanishes at Q double prime. So that means that that this X of Gn will kill this vector. So there is no contribution. Okay. So I am going to this will be first thing. Okay, so this anyway, let me not. I will draw a consequence. So similarly, so let me write other. So you see what I have done here. Let's observe that. So this thing is in the quotient. This object is in the quotient. So this is 0 mod. The quotient. So what I have done now, so X minus n V1 will cover H of mu star because I'm varying over all possible negative n. So for any n, so I'm covering this here. So what I have done, that the second vector here, I have moved it arbitrary such vector to V1 in V of mu star. That's what I have done, right? So this was arbitrary vector in the H of mu star. And now this is 0 here in the quotient. I have moved it to vector only in the top piece. And similarly, I'm going to do the other thing. So similarly, let's take another function Fn. And this is going to be a function of C of sigma twiddle minus the Q prime and Q double prime. Such that Fn by Q double prime minus the double prime to the minus n is congruent to 0 mod Z. So now I'm going to take such a vector, such a function Fn, which has I don't care what it is doing at Q prime and P, but at Q double prime, I have a very controlled pole here. That's what I'm doing. So I have a very controlled pole there. And now if I use that, right? So if I use that, I'm going to get an equation like H tensor H1 tensor X minus n V2 equals minus X Fn H. tensor H1 tensor V2, so the negative sign, and minus H, X of Fn and Q prime on, sorry, what am I saying? X of Fn minus H tensor, sorry, X Fn on H1 tensor V2. So this is here in the quotient. Of RHS. So let's see, what did I do? So actually, I mean, maybe I should have written X of Fn acting on H1 tensor H2 tensor V2. So this will be exactly this plus this plus this. So X of Fn here will be, okay, so X of Fn H. Well, I mean, okay, let me put H1 and H2 then, sorry. Actually, okay, so X of Fn H1, H2, V2. So this is X of Fn H1, tensor H2, tensor V2, plus H1 of X of Fn Q prime acting on H2, and then it will be V2, and then H1, H2, X minus N. See, because this X of Fn has only contribution with exactly one pole, Z prime to the power minus N. So I'm going to get exactly X minus N acting on. Does that make sense? Okay, so this tells us, right, so right, so I'm going to put that in. So this is 2. Okay, and finally, one more thing. So finally, I am going to take, so take F in C of sigma to minus P such that F of Q naught prime, sorry, Q prime is 1 and F of Q double prime is G.
You don't want one both?
No. I want on one point, I want it to be 1, and on other point, I want it to be 0. Okay, so again, let's calculate. So this function X of F acting on H tensor V1 tensor V2 will be X of F acting on H tensor V1 tensor V2 plus X of H tensor. Right, so it will be X acting on V1 and that's it. Oh, no, sorry, I should put V2. Right, because this function is 0 here on the second factor, so no contribution here. On this one, it is So this is the evaluation representation now here. So x and this function is going to take value 1. So this will be just this one. Okay. So now, and this is my so let's see now. So in the quotient, this is 0 in the quotient. And similarly, this is 0 in the quotient, and this is 0 in the quotient. So this is 0, and this is 0. Okay, so let's see now. I am saying that this has moved us to the right place. And right. So no, I have to start somewhere differently. So let's see. So this one is now moved to right. Okay, correct. So that's how I will going to argue. Bear with me. So here, this is arbitrary thing in the tensor product, and this is arbitrary element in the h of mu, the representation for the affine. And this becomes equal to this one because this whole thing is 0. So what we have done, the second and the last component has become V2, and here also it has become V2. So the last component we have now made it to lie in V of mu. So this here.
Sorry, are we fixing a particular mu or because you have to do it?
Yes, that's right. No, exactly. Yeah, you're absolutely right. So I am arguing for every mu.
Okay.
For every mu, I am arguing. So right, I am arguing for every mu. Right. Yes. So very much. So I'm saying that the last coordinate now, last factor, I have moved it to V of mu.
For a given mu.
For a given mu.
Okay.
That's right. That's right.
Okay.
Exactly. Okay. And then by first one, so this is now, so second one is already in V mu. So second one are already in V mu. Now this quantity is arbitrary vector in the h of mu star, and that I have moved it now to V of mu. We agree? So you see, so by the second one, I have moved the last factor to, yeah, so this last factor is this one, arbitrary in the h of mu, but I moved it to V2 and V2. That means I have moved it to V of mu by the second one. By the first one, so first one, this is 0. So this side is V2, V2. I'm not changing that. But this one is arbitrary element in h of mu star, and I have moved it to V of mu star. Okay. And the third one, what it's doing, so now the third one, so this is 0. So V1, V2, and I have now moved it to V2 and only x acting on V1. So at least what we have done so far, we have moved everything to V mu star V mu.
To sum of the V mu star.
That's right. That's right. Exactly. Exactly. That's right.
Sorry, I think what Pierre said is what I didn't understand.
Yes.
You've done it for all mu simultaneously? Because
yes. Yes. Because that's right. That's right. Indeed. See, because I would have taken, see, That is correct, because I would have taken V1 and V2 arbitrary vector in the direct sum here.
Yes. Yeah.
I could have taken arbitrary vector in the direct sum of that.
Okay, but then
I'm not using irreducibility of this thing, right?
confused.
You are confused. Okay, so let's go over this once again. So think of this.
Or maybe Jacob has these.
Yeah.
That as a representation of G cross G, that's a quotient of U of G.
Right.
Okay, so that's, I think, just some statement like that.
Are you coming to absolutely, Jacob? You are absolutely right.
What's that? Could you repeat? That if you, the thing in the brackets there, as a representation of G cross G, it's a quotient of U of G with G.
Right, exactly.
Okay.
I am coming to that. In fact, that's the next step.
Okay.
But I mean, to at least clarify your objection, is that let's take H of lambda, and I'm going to plug this all together here. Okay, and then I'm going to argue. I'm not going to argue individually. I'm going to argue here as the whole thing. Okay, very good. And now, as Jacob already said, so what I am coming to is so now I really not used so far 3 in a serious way, but now I'm going to use it. So now consider this map UG.
Oh, wait, so sorry, Jacob, were you talking about a statement at the level of the usual Lie group or at the level of the affine group?
The usual.
Oh, wait, okay, I'm worried about the affine. So why can you move? So you have a bunch of vectors. Yeah, so there are 2 steps. I worry about the first step. How you're going from you have a bunch of vectors, V mu and what do you call it? H mu.
That's right. That's
V2
right.
mu and H mu, but you have one for each mu.
That's right.
And you want to move them all simultaneously.
That's right.
So
That's right.
So as I understand, what you proved that for 1 mu. Why can you do it for all? Maybe I missed it.
No. I mean okay. So let's see. So
I think one has to use that different new if non-isomorphic.
Right, and we haven't somehow explicitly said. I'm just trying to understand where.
sorry, what?
I think one will use that the different V mu are non-isomorphic.
Yes.
Will be occur somewhere.
I was going to come to that now, but
But I think
even at this stage,
you're saying that we've already reduced to this thing. Is that right?
right, that's right.
So that reduction I have understood because of the same thing. I understood that mu by mu, it's true.
Correct.
Okay.
But
Why
so
can you go from sum of H mu star tensor H mu to sum of V mu star tensor V mu? Like, why can you? It sounds like.
okay. So let's see.
You probably said it and I just missed it.
No. I have not said it carefully enough.
Yeah.
So your objection is well taken, but let's see. Okay. So here I am taking.
Yeah, so that's where you moved one of them into V mu, right?
Right, that's right.
And then you're saying you can do that for a bunch of mu's simultaneously.
That's right.
So that's the step I'm asking about. Why?
No, you are absolutely okay. So let's see. So this, okay, so how to say this clearly? But see, okay. So what I'm saying is that it does, see if, so your objection is that we have moved one mu at a time,
Yes.
right? How do we know that we have moved all of them simultaneously? Right?
For that we can do it, yeah.
Yes. So what I'm saying that
Can't you say that the maneuver explained last time?
Yeah.
You can rewrite the right-hand side of that as something that involves putting representations of the finite dimensional of the algebra at those points. And then you only care abstractly about the isomorphism class of that finite dimensional representation, which is the thing that's in brackets. And the thing that's being used about it is that it's generated by the vector that is.
I think even that will not be needed. Let me try to say it and let's see if you agree. So let's, one mu, I have done it. Let's take one mu out of this set. And there I have moved it so that my two vectors, the last two vectors, are in the finite representation.
Yes, but you could have spoiled previous one. You could have spoiled what you did before for other views.
Is it like, can you just prove it by sort of an induction? Like, you know, that eventually if you hit something with something, so if you take some vectors and you hit it with some elements which have positive degree or high enough degree, they kill it. So if you do step by step, just slowly increasing the degree, and
Yes,
you can manage to avoid spoiling the other.
And using that intercenter of the universal algebra, you can kill one.
Yeah, and
Yeah.
yes.
So,
It's a combination.
right. So if I moved it here in one of them, but now I've secured this position to be here, and okay. I will try to fix this. Unless somebody sees a clear explanation. I mean, what Kira said, it makes sense to me. What Kira said makes sense to me, and that is the kind of thinking in my mind. But whether it's convincing enough.
I think we can suspend.
Right. Let's do that. Let's do that. Yes. Let's do that. Okay. So where are we? So now I'm going to define a map B mu star. Mu. So this is the map, which is, so let's call this map beta, and beta of A is nothing but A acting on I mu in DC. And what is this action? So I mu is a vector here individually, and this is acting only on the first factor and 0 on the second factor. And that will reflect this thing that there is no action here on the second factor of G. So this is, so I'm giving you a map from here to here, which is only hitting the first vector, not the second vector. Now, this map is surjective. So this map is surjective for the region, and I will tell you why. So this becomes, this is a diagonal G invariant here. And then I'm doing the left action here. So, and these are the isotypic components. Actually, Jacob already pointed out this. So I'm just saying what Jacob said. So as a G cross G module, this is irreducible. And not only it's irreducible, different pieces, they are all multiplicity 1. And the image clearly contains this vector, which is spread everywhere. So this might be surjective. Right? Okay. So, and now, so once this map is surjective, I'm saying that 3 will imply that our map is surjective. Right? Because 3 said that if I take V1 and V2 in the last two factors, I mean, this factor is changing, all right, but I don't care. But this one is only acting here, and if I act by X multiple times, I'm just going to hit that. And every vector here in V mu tensor V mu star, direct sum there. Now the direct sum is going to be hit by this vector. So that finishes the proof of the surjectivity. Modulo something which I will try to fix. Okay. Now comes the injectivity part. Yeah, so this is 45 minutes. If you want, I can give you a few minutes of break here, and then we'll come to the injectivity part. So, I will have to think about this so a little bit more carefully. Yeah. Yes.
Like the left-hand side and right-hand side of that can both be written as the Lie algebra homology of G brackets sigma tilde minus P with respect to different representations, where on the left-hand side you would have.
So you are saying that both sides to be realized as Lie algebra homology of one same Lie algebra?
The same Lie algebra, yeah. The Lie algebra.
Right. So Lie algebra being this one? So Lie algebra being this one?
No, the one in the middle of your.
Oh, you mean this one?
That one.
Ah.
So I want to say on the left, you're looking at H lambda tensored with the universal enveloping algebra, like little g.
Right.
And on the right, you're looking at H lambda tensored with this cyclic module given by this finite dimensional sum. And so the justification for the thing on the right is this formula from a previous lecture where.
Yes, right.
And the justification for the thing on the left is just something general about the homology of an induced representation.
Right. So
It's not induced.
yeah.
What's that?
It's goof and of induced.
It's, I mean, I want to say
This one.
inducing from G to G cross G. Like I take the trivial representation of G.
Oh, I have misunderstood.
See, I'm not sure. Okay, so
You're thinking of the list that when we are already reduced to H tensor sum of V mu dual. You're thinking of the list that of in the subjectivity proof where you're already reduced to H tensor sum of the V mu.
Or I guess I'm thinking of just restating the proposition.
correct.
I map some isomorphism. I want to just rewrite both sides as
some Lie algebra homology.
some Lie algebra homology with respect to two different representations. But then the surjectivity is going to come from the map of the representations as a surjection, because this finite dimensional representation is generated by a single vector.
Right. So okay. So see, I don't see how this will act here.
It doesn't act on that, but so you have a representation of the Lie algebra on the far left, which is
Okay.
H lambda.
Correct.
So if I can compute its homology in 2 steps. I can first induce it to a representation of that.
I see.
And then take the homology for large.
So you are saying that replace H lambda on the left side by inducing from this one to G of sigma to the minus P.
Yeah.
You induce that. Okay. So if you induce that, you are not going to change the homology. It will be the same. Okay, so that will definitely give us the right object this side.
I think we're discussing why that induction surjects onto ...
Because if you write it concretely, it's H lambda tensored with the universal enveloping algebra. And the map is that goes to H lambda tensored with this particular representation.
Right. So, okay. And now the question is there a map from here to this one? So the question is, if there is a surjective map here, then we are done.
Put the, not the H of views, but the V of views there.
Okay. So
But then you're also changing, you have to also make the Lie algebra smaller to act
yes.
that way, right?
Yeah, see, this big Lie algebra is not going to act on V of mu.
Right, but you gave us a formula for the relationship between that big Lie algebra and that smaller Lie algebra, trading the V's for H's.
Correct. Oh, okay, use that. Okay, I see. So use that.
Yeah.
Right. So, okay. Okay, so now I'm going to say the following. This one, I'm going to take this object now, and I'm not going to take this Lie algebra. I'm still going to take this Lie algebra.
Yeah.
Okay. And then I'm going to use this propagation theorem. See, propagation theorem will say that this thing is same as this thing modulo this action. So, okay. So the point is that is this map surjective? That's the question. Once we prove that, then I totally agree with what you're saying. So is that obvious? So let's see, is that obvious? So certainly what we have created now actually
Thing on top is H lambda tensored with U.
yes,
Yeah.
right, that's right. So I think
No, I don't see how you can use propagation theorem. This is for one mu only, but not for all the mu's together.
It's the way in which you put the propagation.
yeah, that's what my you see, on this side there is no role of any mu. Here there is all these mu's which are coming up, but at least.
So is it actually false if you try to do 2 mu's at the same time? Or is it just?
No, I think it's no. It will still be true because it's true already for all of them. But if you take some mu here and some other mu somewhere else, not outside DC, then it will not be surjective. So, but actually, I am just trying to. But probably this is the proof somehow. In disguise, it entails exactly this actually. So, yeah, in disguise. Okay. I will have to think a little bit more. I can't say definitely, but it's certainly a good suggestion.
But the hard part of the previous theorem
Yeah.
would be about whether or not the comparison map on the right-hand side is an isomorphism, but just knowing that it's surjective.
Right, exactly. So that you are absolutely right. Yeah, so let me particularly standing at the board, I can't think so clearly. So, but certainly I understand your idea of the proof, and so let's come to the injectivity. Yeah. So I am going to say something, just the basic idea of the proof of injectivity. So to prove the injectivity, we dualize the objects here. So what one is going to do, so I have a map here, and we have proved that this map is surjective, right? And both of them are finite dimensional vector spaces. So now what I'm going to do, I'm going to take the dual, and I'm going to take the dual here, and one is going to prove that this map is surjective. So earlier we had a map here which was surjective, and now I am dualizing this map.
You say dualizing it degree by degree?
No, there's no degree now. See, I'm not dualizing it at this level. I am only dualizing it at that level. So there is no degree now. So I am going to prove, or at least give an indication of the proof, that this map is surjective.
So there's no natural way just to split the map we constructed. I don't know, but it feels right to somehow pair these things, but I guess it's not invariant under the.
No,
I see.
At least I don't see that. Okay. Yeah. So we prove that this map is surjective, but let's just analyze what is this map now. So this map, this object is nothing but harm. So this is nothing but harm of G sigma minus P H lambda to C. That's what this object is, right? And similarly, this object is, so surjectivity is what we are really trying to prove. And this object is harm G sigma minus P union Q prime, Q double prime. And then whatever it is, H lambda, tensor H mu star, tensor H mu C. That's what this object is. And we have to take this direct sum over H. Since it's finitely many, I can take it outside. Okay. So that means that I take some element phi here, and I want to construct an element here. Now, this thing, if I use the propagation of vacua, then this thing is same as harm H lambda V mu star tensor V mu C with respect to a smaller one, G of sigma minus P, by propagation of vacua. I'm taking direct sum. So given a phi like that, we have to construct an element here. So I am just going to give you a map. So phi twiddle is what I'm going to construct here. So the definition is that if I take H tensor, so H is here, and this one is already surjective under UG to, yeah, this one. So this map is surjective, right? So UG to this map is surjective. So let's take H tensor data of X. And I am going to define this to be phi of okay, so okay, I have to explain this notation. Okay, so this is what I'm going to define. So we are given a phi here, and we are trying to construct a phi twiddle here. So I'm defining phi twiddle to be H tensor beta X. So beta X is taking place here in the direct sum. So maybe I just put mu here, direct sum mu here. So I'm defining a map from here to here. So I'm defining phi twiddle of H tensor beta X, where beta is this map, and I'm defining it to be phi of a capital phi, a phi of xt times h, but I have to define what is phi. Okay, so phi is, in fact, it more or less amounts to what Jacob had said. So let me write it, and then you will see. Maybe I will write it. So this small phi is a map from UG to U in working algebra of G Q double prime sigma twiddle minus T divided by G of Q sigma minus P. Okay, so I have to explain this. So this is a Lie algebra. What is the notation here? I am taking functions here which vanish at Q double prime. Okay, so I'm taking functions on the normalization which vanish at Q double prime, and I'm dividing it by the functions which vanish at Q. That means it vanishes both at Q prime and Q double prime. So this is a Lie algebra. So this is nothing but G tensor C of Q double prime sigma twiddle minus P divided by G tensor C of Q. I mean, if you like, I can just put this one and sigma twiddle minus P. So functions which only vanish at, which vanish at Q double prime, but here I am taking those functions which vanish at both Q prime and Q double prime. Okay. So this is an ideal here. So I take the quotient Lie algebra, and I'm going to give you a Lie algebra homomorphism from G to this one, and that will extend to the involving algebra. And what is this homomorphism? Now it takes, so at the Lie algebra level, G Q prime P to G of Q sigma minus P. So you take X here and you map it to XF. What is XF? So F is a function, right? So F is a function here. Such that F vanishes no, f at q naught, q prime is 1. Okay, so let's go over this. So I am defining an embedding of this Lie algebra into this Lie algebra. And this embedding is given by, I take any vector x here, and I map it to this function xf. And what is xf? So of course, this is x from the Lie algebra, but then f is a function here. So it vanishes at q double prime, but at q prime it is 1. That's what we teach. So it's very similar thing which we used earlier. F of q prime is 1 and f of q double prime is 0. That's what we used. And now we take this one, and it does not matter. Of course, there are lots of choices here, but it does not matter. You just pick one of those functions, give this embedding, and extend this to here. So now, and what is xt? So on UG, we have the involution anti-automorphism, which takes a vector x to minus x, anti-automorphism. So now I'm taking xt, I apply phi to that, and then, so this is now happening here. This is happening in this Lie algebra. Okay, this is happening in this Lie algebra, and then I hit with the vector h. So this one, of course, there's an ambiguity there, but since this function a g of sigma minus p invariant are annihilated by that, that ambiguity will go away. Whatever coset representative I choose, it does not matter. So this is the definition. Now here, I am going to leave two checkings here, which is some slightly long calculation. One, beta x. I took beta x to be this function, which of course is far from being injective. In fact, its kernel is exactly the intersection of primitive ideas. So the kernel of beta is exactly the intersection of primitive ideals. So there is a large kernel there, and I'm defining this map by beta x. So one has to prove that this map is well defined. And secondly, it is annihilated by this one. And both of these are slightly long checkings. It's in my book with full details. So in principle, if you want, you can look it up. So, and I think this thing, considering this Lie algebra, is somewhat similar to what you said. I mean, I'm taking u of g and this one, and this is somewhat similar. See, we are taking sigma minus p, and then we are taking this one, and this is what I'm doing, sigma minus p, and I'm taking this one. So somehow, at least morally speaking, this looks similar, but I will have to look into that. So yeah. Actually, anything is
the lack of the splitting is bothering me. It's strange you can't make a map from right to left, isn't it?
Oh, wait, before? Like that you cannot define the map in the other direction?
So you are saying that this original projective map.
Yeah, like I would like to have a map in the other direction by pairing the factors.
You can do it with propagational backward. Because
Okay, can we
start
talk
with,
through this? Yeah.
you start with the bottom, so on the top, on the central board on the top, but sorry, at the bottom left, where you
Okay,
have the
let's
H
see.
lambda tensor B.
So
Tensor
now you are asking,
in this,
let's remove that. Let's remove that. And we have a subjective map, and let's remove
Yeah,
this.
and I think
And now you are asking if there's a map in the opposite direction.
yeah. So let's start with the H lambda tensor B coinvariant model.
Right.
Right.
That's right.
But I'm confused because we're taking coinvariants. Am I getting confused?
you start before taking coinvariants. You have H lambda,
Yeah.
tensor V mu dual,
Yes.
and these maps to H lambda.
Yes, but what I'm confused about is we're taking coinvariants for like two action, V mu tensor V mu star. You don't just have a diagonal action of G.
Right, right,
You have an action of sort of
G cross G.
You have two different points.
right,
But then,
exactly. So,
No, there's no contradiction. It just sort of bothers me.
right,
But
so you,
it doesn't. It's okay. It's not
so
even
it's
a
like, why
question.
is it well defined? Why that map will be well?
I don't like that map. I don't
That
think
makes-
descends to covariance. If
I
I'm
think it-
because he's taking covariance where the group can act differently.
yes,
Thing.
right, exactly. So,
Yeah, it's okay. It's not a real question. I'm just.
no, it's a good question. And
But if I see this as being endomorphism of V mu, can't I just say, oh, can I then fix one?
Doesn't the proof have to use something like the classification of the integrable representations? Like we need to know that those are the mu's that are.
Yeah. Yeah, but what I'm saying is like somehow he's taking covariance by a little more than I would expect. It's like. I don't actually have a formal
Yeah, I
objection.
think if
just-
you have something like, I have to think about it. I think in the paper of Loenka, he tries to give a proof which is more in this
okay.
spirit, like when you have a module which has an action of G by G. So you have and then you quotient about something, it's the same as
Yeah,
quotient by diagonal, or there is some way of relating.
don't worry.
no, I have an answer to your question. I think,
Okay.
So, okay. And basically that's what is going on in this proof also, maybe in a slightly different language. So let's take a vector here. And we want to map it to here, right? That's what we want. So that it goes down to the quotient.
Yeah.
Now, any vector here, I can hit by so any vector here, I can write it like that, where beta is the map, this map. Because this is surjective.
Yeah.
Any element here, I can write it as beta x, right? I mean, beta x is outside, so sorry. So I take this one, sum, and beta x acting on this one. So any element here looks like this. H tensor, H is here, and beta x directs some I mu is here. And this is surjective, so I can write any element here. Now I'm going to map it to H tensor, and let's go back to exactly this definition which I gave you. So let's apply phi of xt. So, okay, right. So, sorry. That's why. I apply. Can you read it?
Yeah.
So now I'm just suggesting, I don't know if it will really work, but I'm taking any h here and any element here, I'm writing it like that.
Okay.
Right? Because beta is surjective, I can write any element here as like this. Now I'm going to map it to h and phi of xt, where phi is exactly this map. Phi is exactly this map.
Okay, so you don't just pair them, but you also kind of fiddle with the lambda.
Right. Now the only exactly. So okay, so my one concern though is here. So this is a function which has pole only at P. I have a concern there that it has pole only at P, but this is not a function on sigma minus P, because the two values might vary. might be different. If they were the same, then of course this will be very well-defined thing. But okay, so this does not work.
Okay, don't worry about it.
Yeah, okay. Right. Okay, so I want to move on to the connection. Unless you have some other, there are so many so good suggestions.
No, we want to hear about the connection.
Certificate?
No, we want to hear about the connection.
That's right.
That's going to be the best part.
Yeah, okay, very good. So I have to do a little bit of preparation. So first of all, I have to talk about the Sugawara operators. Those are the basic objects. So let's see. Now I can erase everything, I guess. So first of all, Virasoro algebra. So this has basis Dn and C bar, where n runs over integers. And the commutation relation, probably I do not need to write it, you all know very well, is d of m minus n. No, sorry, no. M minus n here, and then d of m plus n, and delta m minus n, m cubed minus m by 12, and C bar is central. So that's the Virasoro algebra. And I'm going to define this Sugawara operator.
And if I remember right,
Yes.
the unique the universal central extension.
That's right.
Right. So
That's right.
so
So
if I didn't know that m cube minus m, I could in principle derive.
exactly, that's right. So exactly.
Can I ask about the number 12? Is that normalized in such a way that there's a GM that's like some GM
Yeah.
extension at the level of groups?
I think, okay, the only explanation I know of is because you combine this with the affine Lie algebra representation theory, and the central charge here matches better with the central charge there.
Is it going to be such that we're going to get integers as the central charge out of the?
Yes, that's right. Exactly. Yes, that's right. Other than that, I do not know any other region. See, because if I think of the diffeomorphism group of circle and I take the central extension, I do not know if 12 will come out in a natural way. I do not know that. But I do know that with this parameter, I mean, with this C bar, it works better with the affine Lie algebra theory, which I'm coming to in a minute. Okay, so Sugawara operator. So this is defined for every integer, and ln is half. Let me write it, and then I will explain the notation. Ei j plus n, and this is summation over I and summation j in z. Okay, so what is the notation?
On some integrable module.
Yes, that's right. So let me explain the notation. So EI is any basis of the Lie algebra G, and E upper I is the dual basis. So dual basis, of course, means EI, E up to J, my normalized invariant form, where I take theta check to be 2, length of theta check square to be 2. So this is delta J. So EI and EFRI, that's minus j plus n. So I is running over the basis and j is running over integers. And this is the notation where it means that if this quantity is less than or equal to this quantity, I don't do anything. But if this quantity is bigger than this quantity, then I just switch the order. So this notation means EIK, I mean, it does not matter. XKYL means XKYL if K is less than or equal to L and other way around. If K is bigger than L. So you always want to put the bigger brother to the right side. That's the idea. Okay, so this is an element in developing algebra of G hat. But some completion, to be precise, this is infinite sum, so some completion. So now the point is that element acts on any highest weight module clearly, because this will be a finite sum. Most of the terms will go away. Okay, and then there is this very nice commutation relation. So the commutation relation is, yes, so proposition. So XM ln is C plus H check M times XM plus N. 1 and 2 LM ln is C plus H check M minus N LM plus N plus delta M minus N M cubed minus M by 12 dimension of G times C and C plus H. Okay. No.
Is it big C or small C?
No, this is all big C. See, because right now I am not fixing the central charge of any representation. It's a big C. So, right. So this is big C, and H check is the dual Coxeter number.
Those are identities you had. This is an identity in U hat.
Yes, that's right. Exactly. This is happening inside U of G hat. That's right. That's right. Yes. And in fact, it's happening in not the completed G, but just the Laura polynomial G. I mean, it's completed in U hat, but it's not completed in the Laura series. So here, I am not taking power series, I mean Laura series. So my Lie algebra, okay. So G twiddle is G tensor C T T inverse polynomial. plus C. I am not, see, earlier I took Laurent series. I don't need to take the Laurent series here.
You're saying that the hat over the U is such that the G hat will embed in U hat of G or without the, or of G tilde?
So G tilde will embed in hat.
Does G hat embed in U hat of G tilde?
Is this what you are saying?
That's what I'm asking.
No. See, because, no, that's not true. No. So for example, if I take an element of the form X tensor, let's say T to the power n bigger than equal to, let's say, -10. I'm just making it up. I'm just making it up. Let's consider this element. This element is here, but this element is not here.
So what's the definition of the completion?
Okay. So that brings me to the definition of completion. So the completion is product of so let me carefully write it.
So
So
if you take the sum outside the tensor, it leaves there.
say it again.
Like that element, right? X tensor, this series, it doesn't belong on the U hat G tilde, but if you take the sum of X tensor T to the n, these will belong to the U hat of G tilde. You're quotienting on the right by things like G times T to the n for high n.
But then shouldn't you say that that element does belong because it means the element you're talking about?
Well, you cannot move the infinite sum in and out of the tensor product. So if you didn't have this element before.
Okay, so let me first define it precisely.
And
Then we will. Let me define it precisely and then I will discuss it. Okay, so that's the definition. So U hat of G12. So I'm taking the negative Borel of G12. So that means all the non-negative, non-positive powers. I'm taking that. I'm taking enveloping algebra of that. And then tensoring with U d eta. So these are the degree D elements in the U of eta hat. And degree D means the principal degree. So any element I can write it as, let's say, x1, t1 to the power n1, xd, t to the power nd. So any element here, oh, so this should not be, no. So let's write xp. So I take any element. So this is an element in enveloping algebra of U of n hat. What?
What is n?
So this is the positive part. So n is the positive part. So nil radical of the Borel of the positive part. So this is exactly that's what it is. So n,
You mean Borel or algebraic? Or is it you want the algebraic?
yeah, no, you're right. You're right. So you're right. This one.
Then this sum is in your hat.
Will it be? Will that be there? So if I take x tensor,
One tensor something in this.
so x tensor n So
I think in this story, you don't need to correl at all. You just need to parahoric this.
yes, I could do that. Yes, I could do that. Definitely. That's not going to make any difference. You are absolutely right. Question is this element here? So you're saying it is here?
Yes, one tensor and then I think
X tensor Tn. Yeah, it looks like.
I don't understand why it belongs. I understand that taking the sum outside, then it will belong. But taking it the sum inside, I don't understand.
what's the
why.
difference?
There's no
Well,
difference.
I don't know how tensor of an infinite sum.
No, there's no difference.
But,
For me, I just expand by definition.
No,
but
that's right.
That's the point.
No.
Not expand by definition, then I thought, yeah, this thing it belongs there. I agree.
Yes.
Right. No, you are absolutely right. But
But if I don't make sense of the infinite sum,
Okay,
then
yes, okay. I
But-
agree.
Sorry, I'm confused. That thing doesn't look like it lives in the product that you described.
One tensor something, because N contains all the things with positive T's.
yeah, so you see this is positive. So this belongs here.
But doesn't the tilde mean that you're only allowed Laurent series, not power series? Sorry.
Yeah. This is only yeah, no.
But you complete for that.
Yes, you are completed. It's the product.
But you're completing with respect to D, don't you have to take larger and larger? Sorry, use of D means,
That's right. So this element, X tensor T, so suppose I were to take n plus 10, let's say. So X tensor 10 will belong here.
I guess the thing you were calling, it's not equal. You mean U hat is completion with respect to what is on the right. This makes no sense.
This is the definition.
No. You want to define a completion and you tell what are smaller and smaller subgroups.
what does the use of D mean?
So U of D means that N1 plus NP is D. So UD is not filtration, it's the gradation. And UD, okay, so let's be clear here. So
you fix some basis for the Lie algebra to define that?
not really, just the T power. So any element here, a typical element looks like x1 to the power T N1, xp tensor T and P. Okay, that's a typical element. And the degree of this element, so I'm going to define degree of this element to be exactly N1 plus N2 plus NP. And this consists of exactly degree T elements. So that's the definition. Sorry, I'm sorry about the confusion.
I see, so that element does live there.
Yeah, I see that. I see that. But yeah.
So you're allowed infinite sums where the degree in the T variable is going to divide.
Okay. Yeah, but I'm not sure if this is really an I can define for everything here. I'm still probably it's not so important for me, but I'm still not totally convinced that that G hat, the completed one, it's really sitting here because you maybe that, but let's not. I mean, I'm not. I mean, I'm not so. It's not very relevant. I mean, I'm going to work in this algebra, okay, and there everything makes sense. And the point is that we have this commutation relation where H check is the dual Coxeter number. And you see, this relation exactly tells us that it's Virasoro. Not exactly, because if I divide by this one, so if I fix a central charge and I divide by this one, then it becomes, I mean, okay, you have to be a bit careful because so the Virasoro were without this and without this. And without dimension G. So, okay, I'm going to make a precise statement. So just right. So I'm going to make a precise statement here. So that will, I think, clarify the so lemma. Oh, I switched to that chart. Okay. So let V be a smooth G twiddle module. Okay, so what is smooth? I will define in a minute. Then, no, assume that C acts on V via a scalar C, which is different from negative of the dual Coxeter number. Okay. I don't want that. So then V is a Vir module, Virasoro. I did not give it a Virasoro module under under the action. So Dn corresponds to the action ln divided by C plus H check. This is small c now. So this is this C. And C bar, which is the Virasoro central element, and that goes to C times dimension of G divided by C plus H check. Identity. Okay. Now, what is smooth? Smooth just means that for any vector, it's scaled by high enough power up. That's what it means. So smooth means that for any V in V, it's the action of the positive part is locally nilpotent. That's what it means. Okay, so that's the lemma, that any representation of G twiddle. So for example, highest weight module is smooth, but there are other things which are not necessarily highest weight, but they are smooth. So let's assume that this central charge, central element of the Lie algebra acts on V via a scalar C different from the negative of the dual Coxeter number, because I have to divide by that. Then V is a Virasoro module under this action. And if this representation were unitary, then Vir module is unitary. So the same V becomes a representation for Virasoro. I mean, I'm not changing my V.
So unitary,
yes,
normally means Lie algebra acts in a skew adjoint way.
Right, that's right.
So
exactly.
It's so excused because is there a factor multiplication by I or something like that? You're taking quadratic.
So we have to give you what is the kind of compact form.
Okay, all right, okay, first there's
So-
some real form, okay.
So there is some real form, exactly. So, right. There is some real form. I mean, although it's not going to play any role in what I'm going to say next, but there is a real form. And so there's an involution, I think, which takes dn to d minus n. So there is some involution. I forget exact definition. So
Because the real form is the tangent vector tangent to the circle.
yes, that's what it is exactly. So
ln is Zn then Z by dz.
yeah, so unitary for the Virasoro means dm, yeah, exactly what I said. So dm vw should be equal to v of d minus mw. That's what it means.
Okay. Which I think matches with what.
Yes. Yeah, right. That's right.
Although, sorry, which one is D0? Is it Z
So-
by DZ or D by DZ?
No, d by dz.
Z D by DZ is D0? Which one is it? Yeah, just what's the normalization? That's D0.
Yes.
Okay, then I think that matches exactly what Pierre said. Yeah.
Yes, that's what it is. Right. Okay, actually, my time is up. So I could not even begin
We
my.
successfully stopped you from getting anywhere yet again.
No. This is so good. I mean, you people are the best students I ever had in my life. I cannot imagine any better student in my class. So usually I don't give H plus to all the students in my class, but in this class I'm going to give you all H plus plus.
Okay, oh my God.
When I was
Yes.
in college,
What?
when I was in college, I
Yes.
took a class where one of the section leaders gave a speech like that to our section at the end of the semester. You guys are the best students that I've ever had. But then for some reason I can't remember, I had to attend the next section that he gave after that, where I witnessed him giving exactly the same.
Jacob, trust me. I am not going to repeat this in any other class. So I do not stand corrected. So I exactly mean what I said.
As long as you don't give a final exam.
Yeah.